According to concept functions like that, you put in 100% data, but only a fraction of it is lost.
Right. Yeah, so this is a whole thing, right? So this is the idea of data compression. So this is a whole area. If I can compress, so this percentage example is really great. I can't compress every single file, let's say has 100 megabytes, I can't compress them all down to 1 megabyte. That would just be impossible because there's fewer things that are 1 megabyte large than things that are 100 megabytes. It has to be but you can say, well, most of the time, 95% of the time I can. And that's good enough for those applications. So there's a notion, this pseudo-converse thing comes up with this is like a real issue. So like quantifying how much information. Yeah, like other things people want to check on.
Oh, sorry, I just came today because I have no friendly. I think last time I was here, I was like, when you said yeah, so I guess it's great. I should aim to take my world's like school client.
Wait, you're
8:35. They also have to have insurance that day for but they at least told me that they like laughed about it.
No. I'll post them when I'm able, but yeah, I'd like more detail. And then kids running around under high, so I can post them soon, but not soon. Yeah, so my kids are coming to Friday, and then Professor Tom's kids are coming to Friday, and then so what's kind of funny is we're going to be able to really bring kids. But then Ken Butler, he's a stats professor than me, so his kid is it was like babysit my kids. So she's coming. So we're just going to be kind of busy. I try to call students people. So my wife teaches high school. They're a great guy. Sure. So that guy, the guy in the white shirt there, you should chat with him. These are all just standard, the exact same page. So these are all just standard row operations. You can say like, okay, did they switch 2 rows? No, they didn't switch 2 rows. So it's you have to multiply this row by the inverse of 2 rows over. Okay, there's a lot of people showing up. I have things to do. I don't have that section. Okay. Check the guy in the white shirt. Those row operations do make sense, but we'll put that down. All right, I have 1 minute. I'll be right back. Yep. Bye. Sure. So my office hours are Wednesdays and right, so I'm in 3100. All my office hours are listed in the syllabus.
3100.
Yeah.
So not in your
I'm not in 47 right now. There's too many people who come to my office hours. So all the details are listed in the syllabus. Cool. All right. It is 1:10. Let's make this happen. Yeah, I have to start teaching now. I also teach this class. Yes. Yes. Okay. Hello, everyone. Hello. Oh my goodness, it's Pi Day. That's so exciting. Nice pie shirt. Okay. Be well. Thank you. Yay, Pi Day. Yeah. So Pi Day is kind of like a holiday for mathematicians or something. We get all excited about it. I understand that right now on campus, CMS students are baking pies. Professor Tom is like got the research kitchen in SW and is baking pies there. And then 3 to 5 are going to be doing a bunch of stuff.
So what you're telling me that when he and I were in for the right class in there, we should have knocked on the door and asked for pies?
Yes, that is what you should have done. But don't worry, there's still time. In IA 1100, there's going to be pie activities from 3 till 5. So after lecture, I'm going to run to IA. My family's meeting me there. Professor Kielstra's family is going to be there. Professor Butler's family is going to be there. So it's going to be sweet. So one of the unfortunate things is that I won't be able to upload the notes to this afternoon. So they'll be posted midway through next week. While you wait, there's an absolute banging article about how to calculate pi with physics. Very recent article, 2003, which shows that you can like calculate pi by having a very big ball, so this is ball of mass big M, push towards this little ball of mass little m. They bounce off each other, they bounce off the wall, and the number of bounces just gives you the digits of pi one after the other, which is like mind-blowing. It's so good. So this is probably my favorite fact about pi right now. I encourage you to check it out. Earlier this morning, I emailed all the people who signed up to write the deferred using the course admin form. So they got the room information this morning. There was about 98 people from this class. If you weren't contacted but you think you're eligible, please send me a brief email. I am busy after this class, but I'll be in my office Saturday afternoon before the test, so I can still get back to you. Okay, this week we are going to finish off Gauss's theorem. That's kind of our last major theorem in vector calc. And then we're going to get into differential forms. We're going to do weeks 10, 11, 12 on differential forms. This is going to be theoretically and more theoretically heavy than the rest of the course except for Fourier. Our book doesn't do a great job of forms, in my opinion. The last several times I've taught this, people have been like, what the hell are differential forms? What's going on? So we're gonna lean into that. We're gonna do a more thorough version. The book that I'm following for most of the forms material is this amazing book, Visual Differential Geometry and Forms. You can't find it online. Don't Google it. The PDF is impossible to find. The library also has it. Okay. Cool. Things people want to check in on, things people want to ask about. All right. Let's do some math. Okay, so we got to Gauss's theorem. Gauss's theorem, we're looking at simple regions in R3. I call them simple, our book calls them elementary symmetric. Same difference. We came up with the parameterization of graphs. Notice with this example of a cube, opposite faces have normals pointing in opposite directions. So here on the top of the cube, our normal is pointing upwards in the direction k. On the bottom, we have normal pointing downwards, direction negative k. This tripped some people up during the proof. So when we were going through the proof of Gauss's theorem, the top bound and the bottom bound have opposite orientations, similarly to how the cube does so. Oriented differently, so we got a plus and a minus. Okay, so what's Gauss's theorem saying? It's saying the divergence over a volume is the same as the surface integral over the boundary. Okay. Okay, so let's do a proof that sort of to classify divergence-free vector fields. Okay, so we'll use Gauss to classify those vector fields that have zero divergence. So so suppose that we're divergence free. Okay, so suppose that our surface bounds some three-dimensional thing. We're then going to push this surface integral to the interior of the region. And then going the other way, so how would we make this work? What's kind of the idea here? How could we argue that this then implies something about divergence? I'll speak up at once. There's no rush. It's okay. Take a moment. There's no wrong answers. Yeah, sure.
You can do that using
Yeah, so the sort of idea is, okay, we want, something Stokes, so, yeah, so Stokes would say that we go to the, Stokes is a thing about curl, right? So we'd say, okay, so if we had a curl here, yeah, sorry, I wrote the little statement of Stokes down here. If we had a curl, we'd be in a better spot. So let's say that this thing integrates out to 0 over all closed surfaces, and that our divergence is non-zero sum. Right? If there's a spot somewhere where this thing has positive divergence, suppose for the sake of contradiction, this happens. Somewhere in space we're not at divergence 0. Well, if there's some point where we're not divergence 0, we might as well assume that we're positive divergence. The negative case will be very similar. Okay, so what's going on? Our vector field is like expanding at some point. Things are kind of pushing outwards at that point. What can we do then? Sure. Yeah, we've got continuity because we're a C2 vector field. We're like really nice, we're really smooth. So so continuity, there's going to be some small ball where the divergence is bigger than 0 on that whole ball. I want more space. So our divergence is bigger than 0 on the whole ball. Gauss says that's the same as the integral over vector field of the boundary. the boundary of the ball, that's a closed surface. So we have to integrate out to 0. Contradiction, so we have to be 0 everywhere. Thoughts there? Yeah, sure. Go over to the previous thing? Yeah, sure. Okay. Yes. So this is partially a classification of, so we classified the irrotational vector fields, right? The irrotational vector fields, they're conservative, they integrate to 0 along all closed loops. This is sort of a classification of the divergence-free ones, right? Divergence-free if and only if we integrate out to 0 for all surfaces. Lovely. So we did a bit of calculation. We had a kind of a complicated vector fields. We wanted to integrate it over the surface of a sphere. So we pushed it to the interior of the sphere. We got a nice integrand. We noticed that by symmetry, 2 of the terms would go to 0, right? Every place where y is positive in the ball, it'll also be negative, and it'll cancel out, so it cancels out. And then we get that there's only one thing left to take care of, that's a constant, twice the volume of the ball. Nice. So kind of pushing things to the interior of the ball gave us extra symmetry. Okay. Okay. Just kind of an extreme example. Okay, so what even is this region? So a region is going to be sort of a cylinder, and then it will go between z and 0. There's 1. So if we wanted to integrate something over the boundary of this, we would be we'd have 3 parts to parameterize, right? The bottom of the cylinder, the side, top. So what we'll do is we'll use Gauss to push this to the interior. So let's calculate out the divergence of this guy. So what do we get? Squared plus y squared. This one. Okay, and now, oops. And now things look a lot nicer to handle, right? This is like nice cylindrical coordinates kind of stuff. Let's do it. Let's calculate the thing. Right, let's go over this cylinder. Okay, so again, we've got a constant that's just going to turn into the volume of the thing. Now we have to integrate this over the cylinder. And for that, it seems like polar coordinates would be the way to go, right? We don't want to write our boundaries with square roots and stuff. So this will be 0 to 1. Cool, and then we can do some of the coordinates. So this will integrate to quarter. That. And then volume of W will be any arithmetic mistakes? You guys mixed up. Sweet. So pushing to the interior made things a lot nicer. Yeah, you can imagine this vector field will just be really, really messy over our parameterization, but when we go to the interior, it comes like this. Okay. Last lecture we did a little bit of business getting volumes as integrals of vector fields over boundaries. integrate out x, y, z over a boundary. That will calculate out a volume for us. That's kind of nice. And an analogy with Green's theorem. Cool. All right. Okay. So coming back to the business about divergence-free vector fields, we said, okay, you are divergence-free if you integrate to 0 over all closed surfaces. Nice, lovely theorem. What's F? So last week we did the classification of irrotational vector fields. They're all gradients. Now we turn our attention to the full classification of divergence-free guys. So we know that divergence of a curl is always 0. We check that. This is essentially equality of mixed partials. So we know that all curls are divergence-free. All right, great. Could there be any other divergence-free vector fields? Right, we found that all the curls are divergence-free, but could there be others? And it turns out that no. These are somehow the only examples. All examples of divergence-free vector fields are actually curls. Kind of a nice theorem. So let's do it. So someone hands you a divergence-free vector field. You then need to produce something that has that as its curl. And there's a sort of a magical recipe for it. Let's do the recipe. Okay, so someone hands you F1, F2, F3. You can then feed it into this recipe, and this will give you something that has the right curl. Okay, so let's check that. So what do we need to do? So we'll calculate, so this guy is 0 conveniently. So let's calculate out the remaining terms. So we're going to get what this will be minus partial z g2. And then we can go back to our recipe and say, okay, what are our derivatives. So, I'm very, very zoomed in. Right, so we go back to the recipe and we say, okay, what's the derivative of G2 with respect to Z? Well, it will be minus F1. This is going to be minus F1. What's the derivative of G1 with respect to Z? Notice that this is constant in Z, so we don't pick up any Z's here. All we get is F2. Okay. And then we're left looking at this term. Okay, so the first two work out nicely. So far, so good. Now we just have to calculate out this last guy. Where do I want to put this? That's all full. Okay, so our last calculation is this mixed partial thing where we use both components of G1 and G2. So we get something like this. Okay, so what do we do? Now we've got these kind of sort of tricky terms, right? We've got a derivative of an integral. What on earth do we do here? Yeah, sure. Yeah, move the stuff inside the integral. So we're going to get this integral. we've got a Y, a Y. Okay, so notice that these guys have matching bounds now. They almost have matching integrands. Okay, so this is getting pretty close. This is looking pretty nice. So what's our goal? Our goal is to eventually use our divergence hypothesis somewhere, right? We really ought to use divergence somewhere. Now, we don't have divergence quite yet. We're missing a term. We're missing a F3Z term. Okay. We've got some business with F3 though. So what do we want to introduce to make this thing cancel out? Yeah, sure. Yeah, we'll do an add and subtract kind of move, right? And the goal is, okay, well, we've got kind of one part of, okay, all right. More concrete. Okay, so we're getting pretty close. We've got one of these guys. So we can rewrite this guy in terms of the remaining two. Okay, so this guy has the thing that we're looking for in it. Cool. So, yeah, so the add and subtract we want to do is we want to add and subtract copy this guy. And of course, we go to the paper again. All of you are just going to be so scrambled now. Before we do the next move, do people have pictures they want of this thing? We're good? We have what we need? Great. Okay. So rewriting this guy using fundamental theorem of calculus, we get the missing terms to complete our divergence. This then integrates out to 0 because we're a divergence-free vector field, and then we get the F3 that we, the magic works, everything is nice. Where do I put that? Put this here. Yay. Okay, so every curl is divergence free, and every divergence free is a curl. So same set. Okay, what are we up to next? Okay, our last kind of example of Gaussy kind of things is this wonderful theorem. Our textbook frames it in terms of electromagnetism. For us, it's just going to be a nice calculation or a nice topological thing. So what do we say? We say, suppose that Gauss's theorem applies to a body W, and that the origin is not in the boundary of W. We then consider this radial vector field, and we get the following very nice fact. If the origin is not inside W, then we integrate it to 0. If the origin is inside W, then we integrate it to 4. Okay? Super duper duper nice. So this is saying that integrating vector fields over boundaries can detect topological stuff. And I think the physics intuition here is something like if you have a point charge inside W, you can pick that up as the flux on the boundary of W. So if you've got like an electron in a big ball, you can pick that up just by looking at the boundary of the ball. Cool, so this is a big grind. We will do this calculation after the break. Once we've done that, we are done our classic vector calculus stuff, and we're going to head into the land of differential forms. Okay, so hopefully we get there. Let's take our 10-minute break till 2:10, and then we'll finish up this calculation. Of course, I'm always around if you want to come by and chat. I'm happy to chat. Oh. Hey, what's up?
For the kangaroo thing, is this still working?
Yes, so the situation is kind of unfortunate though.
Yeah, I think like 130 buses.
Yes, so what happened was, yeah, we had 100 volunteers, and then the 30 people we emailed to be like, come to orientation today. So did you get a room and all this stuff, or no?
No,
No,
yeah,
okay.
it's okay because to be honest, my schedule is very busy. So,
Sure.
yeah,
So don't worry about it. We're going to keep your stuff for next year so that we can we'll contact the volunteers.
and also Parker, for everyone to who is really
Oh, you don't have solutions yet? Okay, I should email the solutions. Okay.
So-
So they're pre-written. I just have to send them from my computer.
Okay, so it's okay that we didn't mark it.
That's hey, what's up?
Okay, I'll ask a question about today's volunteers.
Sure. So did you get the room information for 4 to 5 today? Okay, so you're in the 70 people who volunteer, but Kangaroo doesn't want to. So I'm sorry about that. So what we've done is we're going to keep your volunteer information for next year, and we'll contact you again. Okay? So I'm sorry about that. That's hey, what's up?
I just wanted to talk more quickly about these versions of green stokes and gases steering wheel.
Yep.
And this one, I remember from last year, this was defined as the hybrid normal.
Yeah.
Is this also the hybrid normal?
So this is this tricky thing. So in the plane, you can just like write down a formula and be like, there, there's the formula.
Right.
Here we didn't write it down.
Right, it's not necessarily.
Oh, yeah. So you can do this. So this will be for both surfaces. Okay. Yeah, you can. So this is
You're missing the thing.
Stokes is around. Careful. So Stokes is around the boundary of a surface. So Stokes there, we're going to have this kind of thing as your yes, and then in Gauss, you want to be effective.
Right, we need to convert it to the scalar form and multiply it by the
Sure. So did you get contacted with yesterday? So then you're in a group of 70 people who said we can't have as volunteers, so I'm sorry. So we've already contacted all of them. Okay? Thank you. So that will be between the end of classes and the day of school. So that's after Friday of week and before Wednesday. So what I do is I have a big spreadsheet of program requests. Monday, Tuesday, I just sit and look at all the Right, so these are different kinds of things, right? This is divergence of vectors. This is a vector form. This is a divergence is scalar quantity, so is vector quantity. So these are different kinds of things. They shouldn't be. So this is a formula for converting a path integral to define internal to that.
I mean, I guess it's kind of physics related. Like, if you want physics and environmental science, well, that's what it's like, is it? Yeah, it is. My dad.
So we can convert this. This is just over 8 years.
Yeah, I applied for this one co-op job board, so really actually not. I'm really happy. I've also been off the line where like
So notice that we lose the vector. Right, this is a vector thing, this is a scalar thing.
but this job's environmental system.
Yeah.
But that's
the kinds of objects being compared here are not the same. Like, okay, here, write down the chain of inequalities that you think is true, and then maybe we can look at it very carefully. Yeah, so write the chain of, I guess it's like 3 or 4 inequalities that you want, and then I can check, okay?
one is 2-dimensional, one is.
That's my guess, but write it out and I can check it. Yeah, let's see. I mean, I'm curious about this thing. My guess is that you're not going to. You're saying you're these 4 things that are all equal. You could write it out. I could check. Okay, so write it out and check which one is not equal.
Just had a question. Did you, by any chance, have the chance to take a look at the updated one? Because I don't know if okay. The first one had a chemistry.
Yeah. So
But the second one is.
And I've just been dealing with Hebrew and Trump stuff. So, at this point where you thought, I can't remember the exact notation. What did we? Yeah. So what's the last? What's the next to last step? We've got this path, this small.
Yeah.
So you go. This path. I think.
So this would be the pass.
So yeah. So okay. So you reached this stage. So
the pass is arbitrary.
right. So I think there's an interesting rule here. Why can we? So why does this imply? So I like it. I like the proof, and I think the only thing that's missing to make it like super rock solid and like when I put this in lecture notes is I think to make so like physical intuition is if you do this for any path p, then they have to be equal. I think the move that's missing is really this is something that averagers who are the same.
Another Irish band.
Trying to make this very, very small. So I think the machine learning works.
So basically instead of saying over the whole pass, show the small children for all three small children.
So I like it. I like the proof. I think it's good. But to make it fit within B42, there's this question of like why, like we've never done this. Like if two integrals are equal and integrands are equal. We haven't done that in this case. Maybe that's like if this is smooth, but
No, it's more like that makes sense.
yeah, it makes sense. And I'm just trying to figure out if I get like reverse. I think the move is we do this with like average value or mean value and something. I haven't figured it out yet, so I haven't figured it out. Cool. But yeah, it's good.
Should I implement this?
See if you can make it work. Yeah, I mean, try this out. See if you can make it work. Yeah, anyway, I think this is a lot nicer than the like construct these complicated maths. So I want to get this to work because the complicated maths. It looks like you're waiting for me. So today I'm super duper pumped. Because it's Friday. So right after lecture, meeting my family. What time did you do? So Tuesday I'm super duper free. Yeah, so did I say we should be Friday after lecture today? I mean, if you're done with me to Friday, what's the observation? So I can't walk you through the so this is the correct parameterization. You didn't say why this. Why would you choose this? But the other one I can walk you through. Tuesday is better, but you also do this. Just email me and say, hey Burger, you got messed up by Monday. Let's figure out a different time.
Okay. Alright. Okay. Let's pick it back up. Let's keep moving. Okay, where did we get to? All right. So Gauss's law of electric charges. Kind of a nice example of sort of vector fields picking up kind of interesting topological information. So the move here is we want to use Gauss. So we want to say, okay, well, this is going to be integral over W of the divergence. Oops. Okay, so this would be over the volume, so we need the divergence of this vector field. And it turns out that's quite messy. So the thing I want to point out is notice that if W doesn't contain the origin, then this vector field will be nice and smooth on the region. So. Okay, so if we don't contain the origin, then our vector field's very, very nice. If we do contain the origin, then we're going to have to be super duper careful. Right? We have to carefully avoid integrating around the origin. Everything will blow up. Okay, so what we need is the divergence of this guy. To get the divergence, we're going to switch to the previous page and do kind of the long calculation there. And then we'll come back to this. Okay. All right, let's get the divergence of this thing. So our theorem is that this will turn out to be divergence free. So let's do it. Okay, so our vector field looks like this. Okay, so we're going to get just the divergence of the x terms. Everything else is kind of very symmetric, so once we have that one, we'll basically have all of them. Right, so. Okay, so what do we get? Okay, so now this is just a normal partial derivative. So we get something like this. We can factor out a norm on the top and bottom. So comparing things to our goal, we're looking pretty good. We've got this 5 halves here. Split up. So this is going to be so we've got the right kind of term here. That looks pretty good. Going a little bit strange with this x here, though. I'm expecting a squared there. Did I miss an x?
Yeah.
Oh.
On the second line, the 2x squared because the original x wasn't derived.
Sorry, say again very carefully.
There should be another x there because you put the derivative of the bottom side.
Right. Oh, so I'm taking. One second. Okay, so quotient rule strikes again. No. Ah, right. Okay. Right. So I've got my numerator times the derivative of the denominator. Sweet. Here. Lovely. Okay. Cool. All right. Love it. Beautiful. Okay. So our x terms work out the way we expect. We then sum this over all the variables. We're going to get 3 copies of this guy. We're going to get a copy of x squared, y squared, and z squared. Cool. So we get 3 copies of this term. We get an x squared, a y squared, and a z squared. That then gives us this guy. Good. And these 2 terms, these 2 guys are equal, right? If we cancel our norm squared on the top and bottom, we get 3 minus 3, so we get 0. Okay, so this vector field is divergence free away from the origin. Beautiful. Okay. Things people want to check on, ask about? Okay, cool. So away from the origin, we're divergence free. Love it. All right, so coming back here, we know that our divergence is now 0. So this will be equal to 0 dV if the origin is not contained in W. Its boundary. Cool. Okay, so if we contain the origin now, we have to be a little bit more careful, right? We can't just integrate because this vector field will blow up at 0. Okay. Okay, so now we have to treat the case where the origin is contained in W, and the move there is we can surround the origin with a small ball, and the remaining integral will just go away. So. So now, if we think about W without that ball, we can use the preceding, so. Or here, I should say. So we can kind of split this integral up over the stuff where we're 0 and then this non-zero thing. Okay, and now we can say, well, what's the integral of this over the boundary of a ball? So looking at just the boundary of the ball, all our integrands become rather nice and we can evaluate. Okay, so let's do that. Okay, so our norm here will be epsilon cubed, right? Okay, and now we have to be a little bit careful with our norm, or sorry, our normal vector. Right, so our surface is this guy. So we want to rewrite our normal vector somehow in terms of R. So R is x, y, z, and its norm is epsilon. So we want something of norm 1. So what we're going to do is we're going to divide this guy by epsilon. Okay, now we've got a norm squared. This is no good. Oh, no, we're good, we're good. Okay, so our integrand is constant. It's just always 1 over epsilon squared. Beautiful, we love it. We're integrating this over the surface of a ball. The surface of a ball has radius, or has surface area 4 pi r squared. Yeah, and we get 4 pi. Okay, so in the event that our region W contains the origin, we can say, okay, well, carve out this small ball around the origin. The difference between that ball and your whole shape, well, your thing's divergence free over there, you don't get any difference. So the integrand is all the contribution of the region around that small ball, and the integral over that small ball winds up being 4 pi. So we get this guy comes out to be so we can kind of measure, we can use vector fields to measure, okay, is the origin inside this object? Is it not inside this object? Cool. Okay. Things people want to check on, ask about, things people are curious about? Onwards and upwards. All right, I'm going to plant some seeds. All right, where are we headed next? We are headed to the theory of differential forms. Yes, let's get into it. Oh, this is going to be such a nightmare to scan. All the backs of pages are full. All right. Cool. All right, so what are differential forms? So we'll talk about this, we'll kind of plant some of the seeds, and then next week we'll build up the theory. Okay, so this material is kind of lightly covered by Marsden and Trauma. They do an okay job of it. historically, when I've taught this stuff, people kind of wanted more details, so I'm trying to build in another week of details, and we'll see how that goes. Our goal is to get to this theorem. So what's this saying? This is kind of our general version of Green's theorem, Stokes' theorem, Gauss's theorem, right? This is a derivative over a region, right? The derivative of omega over a region R is equal to the integral of the original over boundary. Right, and that's kind of our feeling of what all these theorems have been saying throughout the course. Okay, to do this, we're going to need to build up a theory of differential forms. The idea is that differential forms measure stuff, right? That these d omegas are some kind of taking a measurement of a box or a measurement of an area or something like that. We're going to study them from the perspective of linear algebra, so we're going to do some kind of linear algebra heavy stuff. So the first thing is a one form. What is a one form? So a one form is a linear map from Rn to R. It's a thing that measures vectors. Okay? So we kind of care about this sort of special family of linear maps. Okay? So these things are hard to picture. With a vector, we just know what it is. It's a little arrow. One helpful way of visualizing a one form is the following. Okay, is this kind of level sets approach. So you say, okay, well, this is our omega equals 0 level set. Omega equals 1. -1. So what these things are doing is, oh, you can't see the picture. So what is a one form doing? It's giving you a means of measuring things. So if you give me a vector, if you give me a vector, I can then tell you which level set that vector is in. Okay, so one forms are these kind of families of tools for measuring things. And we're going to develop, like, okay, what are the tools for measuring areas and this kind of thing. So how can we think of them? We can think of them as families of level sets of linear functions. Okay, sweet. Okay. Very, very common construction is the following. So if someone hands you a vector, at V, you can then make a one form out of that vector. So you can say, okay, well, I need this thing to be linear, so right, so we want to say, okay, is this thing really linear? Well, well, our inner product, it's a linear thing in both its arguments. Yay, so we have a one form. We have something linear. Okay, yeah, sure. Yeah, it's multilinear. It's linear in both its arguments. So we picked one of them. Okay, so what's the picture here? The level sets here are the things orthogonal to V. Right, so we fix some vector V, and then our level sets come out like this. Okay, so lovely. So we've met a one form before. We've met a linear function from vectors to real numbers before, and that's our so-called gradient one form. Okay, so our gradient one form, what does it do? It takes the directional derivative of f in the direction v. Okay, so we're going to write this with this notation df of v. That's okay. Another notation I think we used is this, but it's fine. It's an inner product. Okay. So this will be linear in the argument v. So we'll get a linear thing. Now, this is kind of blurring the distinction between a single one form and a one form field, right? As x changes, this guy is going to change, so dfv will change. Okay, so it's really a one-form field. So how do we imagine a one-form field? It is something where at each point we have a tool for measuring. So, so at each point, this gradient will change. Right? But if we fixed a particular point, at that particular point we would have like a one form associated at any particular point. Okay. And then the level sets of the function will always be tangent to the level sets of your one form. Does people want to check on, ask about? kind of physical, oh yeah, go ahead.
So the circles are the level sets of the function, but then the tangent lines are the one form.
Yes, so this is, so yeah, this red stuff is the one form. These are the level sets of the function. Okay, kind of intuition question. As you move away from the origin, does the one form get closer together? Does it get narrower, or does it spread out? Do those level sets spread out, or do they get closer and closer together? Yeah, they get closer together, right? So as we move away from the origin, this vector is going to get bigger in magnitude, so the level sets are going to get kind of smushed together as we go out. Okay. Cool. Love it. Beautiful. Okay. So now we can start to talk about this business of dx's and dy's. Right? These things that we've been seeing since high school calculus, what are those guys really doing? What is dx as a one form on R2? What's going on there? Well, x is a function, right? So what does the gradient one form dx do? Okay, so let's give a little bit of notation to our vectors. Okay, so this is the inner product of gradient x with v. Wait, so before we finish the calculation, we should think dx is a tool for measuring stuff. It eats vectors. What should dx measure for a vector? It should probably, we hope, measure the x coordinate. That would be nice. So let's see, how does that work? So we take our gradients of this guy, so this is the gradient of the function x. Okay, we take it in our product, we get v1. Okay, so what is dx as a one form? dx is the guy that measures changes in the x direction. Okay, lovely. Okay, so, so as a vector space, so we can now add and scale one forms, right? That's nice. We can take linear combinations of one forms. This gives us a vector space then. Right? This gives us a space of one forms. going to call this the following weird piece of notation. Right? This gives us a vector space that we're going to call wedge 1 of Rn. And this, as a vector space, has a basis of the dxi's. Any linear function you give me, I can write it as a combination of these Cartesian ones. So right now this wedge is kind of unmotivated. You're like, why does it look like that? What's going on there? We're going to later get to something called the wedge product, which will do all the calculus for us. But we're not quite there yet. Okay, so the one forms have this Cartesian basis. I guess I should also remark so this is just going to be dimension n. Fine. It's interesting to note how these things add together. So let's look at sort of pictures of a couple of these and see what happens. Okay, so we'll draw our two basis elements. Okay, so these are our dx level sets. Okay, and then we'll draw the dy level sets as well. And now when we, so these are like two kind of orthogonal tools for measuring things, right? The dx's and the dy's. When we combine them together, we get a new way of measuring things. My spacing isn't very good. So what I want to point out is that these are vectors. The way we add them is somewhat non-obvious, but it's easy enough to calculate. So if we say, okay, right, let's say we plug in a Cartesian vector v. Our second basis element will output the second entry of v. Our first basis element will output the first basis. Lovely. So these will be things like v1 plus v2. Getting a sense for what the vector space structure is. Okay, sweet. All right, let's finish with one last bit of calculus, a helpful thing for next part, which is that these guys obey a version of the product rule. All right, so what do we have? Right, so the gradient one form of a product, well, that's just the gradient of a product of two things, basically. So this is going to be let me split up with linearity. So at the one form level, or at the one form field level, we have this kind of nice product rule for things. Cool. So where are we headed in the rest of week 10? We're going to play around with combining these. We're gonna, so we've got one forms. Okay, what are two forms? By the end of the week, we'll be able to do like, where does polar coordinates come from in kind of a Jacobian free way? Yeah. Sorry, yes, this is the important question. This is multiplication. So FG is product. Come on, I think people are sort of packing up and we can chat. Cool, so it is Pi Day. I hope you all get a slice of pie. I'm headed over to IA. There's something going on in IA 1 or 1100, I guess. Yeah. So yeah, we can chat.
It's heading to IA, right?
Yes.
Okay, I'm off with
Sure. Great.
Where's the sketch for?
No, they should be straight lines.
It should be straight lines.
Yeah, I should have printed off the grid beforehand.
Ah, okay, so it is just like. But the x plus dy, isn't it just like v0, v10 plus v20? Why is it something like this?
Yeah, so what is interesting, so what is neat in my opinion, is here the level sets have distance 1 between them. Here they have distance 1 between them. Here they have distance, I think, 1 over root 2 between them. So the level sets squish and get closer together. So yeah, this is the calculation that you're saying, that you should just add up V1 and V2. Yeah.
Yeah, I'm kind of getting this.
Cool. Hey, what's up? Yes, so this is like a glorified interface. This is the dual of this thing.
Hi, Parker.
Hey,
How are
what's
you?
up? Hey.
We have an exam here.
Okay, good. Well, we will get out of here as quickly as possible. Also, so one moment, we should probably like erase the boards for now and then ready for those searches, but I'm happy to keep it. So
It's just the RN is the vector space, but then say we're working with like this basis.
What?
So, okay, so let's erase the boards and then we'll handle that question. Oh no.
You want to set up the? Okay, I'll set up the.
Where's my jacket? Let's go.
Let's go.
What's the turn test you've got? Chemistry? Okay, good luck. Oh yeah, it's gonna be busy. And it's all scantrons?
Whatever, just.
Interesting. Yeah, I've been doing a lot. Okay. Okay, let's go hang out with them and chat. There's a lot of people who want to chat, so.
Could you just stand here, just make sure that the exams are not being, yeah. Yeah, I was gonna be.